and is also associated with Center for Industry Collaboration and Sponsored Research ICSR. Sir has earned PhD from IIT Delhi and postdoctorate from Taiwan. His research interests span microwave and millimeter wave integrated circuits, broadband and reconfigurable antennas, RF MEMS at millimeter and sub-millimeter wave frequencies. Dr. Day sir has authored several publications and holds patents and is recipient of prestigious awards including the Serve Early Career Research Award. Sir, we now invite you to kindly begin with the session and guide our participants with your learning, sir. Thank you very much, sir, to accept our invitation. Over to you, sir.
Thank you very much. So let me share my screen. Just a second.
Yes, sir.
Can you see my screen? Is it?
Sir, give us a minute. We are making you a presentator, sir.
Okay, sure.
Yes, sir. Now you can share your screen, sir.
Okay. Okay. Can you see my screen now?
Yes, sir.
It is visible?
Yes, sir.
Okay. And if I change my slides, can you see it?
Yes, sir.
Okay, fantastic. Okay. So let us begin then. Okay.
Please.
So
Yes, sir.
yeah, very good morning to all. So, and first of all, thank you very much for your kind introductions. So I'm here to present some of my works on the FSS, frequency selective surface, as this faculty development program is pertaining to the recent trends in frequency selective surface designs for 5G and 6G applications. So I have prepared my presentations in such a way that it is basically fitting towards the verticals, whatever you are having, but slightly to some advanced, or I would say current state of the art methods for FSS designs. Okay, so maybe you guys have some kind of an idea about FSS, some basic ideas and other things. So my intention is, if somebody is starting to work on the FSS, what should be the current state of the art, such that some of you may get a problem statement out of my presentations, and it may help you in your subsequent career, be it a master, be it a PhD. Okay, so that is my intention. So let us begin with the discussion. So as you all know, I am from IIT Palakkad, and currently I am leading a group of microwave and radiation lab. So let me give you a very brief overview about this lab. Currently we are having three faculty members working on RF and microwave in this lab, followed by you are having around 13 PhD students and few master students. In short, we call it as MRL. Now the kind of topic that we have been working in these groups are as follows. As you know, we have been working on the electromagnetic metamaterials and frequency selective surfaces. Then we also work on microwave imaging and sensing. We also work on different varieties of primarily broadband and reconfigurable antennas, in addition with MIMO antennas. We also work on the RF wireless power transfer, mostly for the detection and sensing purposes. In addition with, we also work on radio frequency micromachining circuits for terahertz applications. So these are the 5 verticals on which my group is working on. Now to begin with the discussion, what would be the theme of today's discussion? As you all know, the theme is FSS. In short, it is in full form, it's called frequency selective surface. So what are the things that you are going to discuss? First, obviously, I'll give you the introduction, and then I'll give you the multiband FSS. Then we will be talking about the higher order FSS. and then we'll be talking about multifunctional FSS design. In addition with, I'll give you an applications of the FSS with respect to antenna, followed by references. Now let's begin with the discussion. Why we need FSS? You can look at my slides. It's perfectly fit towards your. Actually, I like your theme of this FDP. That is FSS for 5G application. Most of the FSS are basically used for conventional communications. But whenever you are talking about 5G and 6G communication standard, you have to follow some protocol, right? Because whenever you are talking about 5G, your frequency point of interest is fixed. Whenever you are talking about the 6G, your frequency spectrum has changed. Now the question, one question that let us ask in the beginning, wireless communications, if you are trying to make for 5G and beyond, where does FSS fit in? Okay, that is the question probably that you are trying to answer, trying to get an answer of these particular questions throughout this webinar. So keep this question mark alive in your mind unless you don't get a reply for it. Okay. So now where does FSS fit in? You can see the 1G, 2G, 3G till up to 5G. The only thing that is continuously changing is the data rate. Now, you all know from the Shannon's theorem that data rate is actually it is the function of the bandwidth. So probably if somebody is dealing with a broad band of signal, obviously it would be giving you much more data rate. But is it always necessary or is it always possible to get the broadband of spectrum for any applications? Suppose one can make the FSS as a broadband, but simultaneously frequency selective surface should also be a broadband. Nevertheless, if whenever you are making as a system, you are not thinking of it as a single antenna element, you will be making it as an antenna array, right? So in that case, you need a power divider. Sometimes you need a coupler, sometimes you need a circulator, and also sometimes you need a phase shifter. So in that case, everything has to make it as a broadband, make the system challenging. And that is the one of the very important problem statement. How to make entire phased array system as a broadband. Now let us see that. What is the applications of 5G? Just to know, it is basically enhance the mobile broadband communication system. It would give you the massive machine to machine communications, and obviously it will give us reliable low latency communication. Now there are multiple ways of doing it. Nowadays IoT is being used, artificial intelligence, augmented reality, everything is used. So what is the purpose? FSS has many purposes. FSS can be used to capture the signal. FSS can be used to make it as an absorber. FSS can be used to change the polarizations of the signal, and also FSS can be used for the spatial filtering application, because inherently FSS will give you some kind of a filter, right? Filtering applications. Question is how an FSS based things will help us to get the filtering applications. Let us see that. Followed by, if you think of some kind of a nowadays, you can see that the active FSS or active meta surface playing an important role. Why it is paying so much attention? The reason is that if you look at the active FSS surface, you can see these you can simultaneously control the beam at your desired location. So you may not need a comprehensive transceiver model to tune the beam. Okay, just by playing on the surface or just by manipulating the electromagnetic wave phenomena, you would be able to tune the beam at different direction. Correct? So now question here is that one can always do it with the help of a phase shifter and antenna. But here you are designing the FSS unit cell in such a way that you can tune the beam. That is conventional FSS. Now what are you doing? Why you are calling it as an active FSS? Because here you are using the diodes as well as you are using an amplifier, by which you are making the signal, improving the signal strength. And also if you look at it with respect to a system, you are actually improving the signal to noise ratio. So by which you can change the beam locations or beam point at your desired direction without compromising the quality of the system. That is all about the current need. Now let us try to understand. some of the key features of the 6G network, because your FDP also covers the 6G. So now, if you think of making an FSS only for 6G applications, you have to be careful about the higher data rate. 5G provides 1 Gbps, 6G provides minimum 10 Gbps data rate should be their minimum in Indian scenario. Okay, obviously data rate followed by low latency, broader coverage, more reliable communications, and lower energy consumption. Now, all you can achieve, but important thing is the lower energy consumption, right? Now, whenever you are applying many active elements or many pin diodes or something like that, obviously you are basically loading the surface a lot, right? Now, whenever you are loading the surfaces with lots of other components, obviously speaking, your power consumptions or energy consumptions will be a challenging issue. So, how to mitigate such things? That could be a question mark. Now, let us see that about the introductions to FSS. So this, whatever the slides that I presented in the beginning, that it is basically giving you the motivation why one should learn and work on the FSS for the current need. Okay. Now, to understand the FSS, what is FSS? First of all, it is basically a periodic structure that can be a 0D, that can be 1D, that can be 2D, that can be 3D. Whenever you are talking about what is 0D, 0D is basically like whenever you are playing with a simple RLC circuit model. When you are introducing the transmission line theory, right? Whenever the structure is becoming a planar using some kind of a PCB process and other thing, it will be give you a 1D method. 2D when you are basically playing with X and Y. 3D when you are playing with X, Y, and Z direction. Needless to say, FSS is one comes under the 2D category directly. Okay. In addition to that, FSS can also come under the 3D category also. Okay, but most of the conventional FSSs are basically working on the 2D category, which is in line with your EBG, electromagnetic band gap structure, other metamaterials or metasurfaces and other things. As you all know, the FSS is basically one of the subset of the metasurface. Here you don't need to follow that epsilon mu has to be negative, blah blah. No, okay, you have to see the, but something you should be careful. What are that something that you are going to see? Now, whenever you are making the 3D modeling, you have to be careful that it is basically the function of the general Maxwell's equations, and you have to apply the Floquet theorem. Rather, Floquet theorem has to be applied to all the FSSK. I will explain what is Floquet. Now, as I said, this is the 3D model, 2D model, and this is the 1D model of the FSS. Now, with this, what is the electromagnetic wave phenomena? Now, if you consider this is an FSS layer, when the signal is falling to the FSS structure, some of the signal is reflecting back, some of the signal is transmitting. Now, if you look at it, as you all know, everywhere it has to be the right-handed coordinate system. Now, whenever the signal is falling, it's basically perfectly following the Snell's law. And now, after that, you are making this surface in such a way by which you will be able to play with reflected and transmitted signal. Okay, in one time, if you are making it as an absorber, nothing to be transmitted, everything should be absorbed. Obviously, reflected signal would be very less. That point in time, it is actually working as a impedance matching surface. Now you are matching the impedance of the surface with respect to the air environment, that is 377 ohm. When you are making it as a polarizer, that point in time, if your signal is linearly polarized, falling into it, reflected signal would be either reflected signal would be circularly polarized or transmitted signal would be circularly polarized, depending on whether you are making the surface as a reflective surface or transmittive surface. Both are same. I'll tell you how. Now, this absorber part I have just said. So now what is happening whenever the signal is falling into a surface like absorber, then you have a reflected waves from the surface. and you have a transmitted wave simultaneously. And you are calculating the reflection coefficient and transmission coefficient, and you are trying to calculate what is the absorptions of the electromagnetic wave in terms of the destructive interference, in terms of the presence of the some of the resistive element, in terms of the intrinsic losses associated within the surface. This is all about the absorbing concept. Now, things can be used as a polarizer, as I said, but also thing can be used as a filter. What is filter? Filter here is basically like, as you know from this response, from the transmission coefficient versus frequency, this response is, as you know, it is a band pass response. You can call the y-axis is your S21, x-axis is your frequency. Your response should be like this for band pass. Your response should be like this for band stop, right? So now this is, you are basically controlling the electromagnetic wave without changing the property of the wave. Okay, you are, what are you doing it basically, rather I would say you are not manipulating the signal, you are basically acting it, making a surface which will act as a filter, and it will give you the required amount of signal whatever you want. That surface can receive a wide range of spectrum, but the surface can only give you the only the signal that you are looking for. That can be in a band pass mode or that can be in the band stop mode. Followed by what is the concept of all the concept over here. Now let us try to understand the concept first. Okay. Now what is happening? First, you are sending the signal incident wave. You have the reflected wave. It has to follow the Snell's law. Theta I has to be equal to theta r. Now, it is happening when it is an air conducting interface. When what is happening to the air dielectric interface? Obviously, because it is not a conductor, it is a dielectric medium. So obviously, some of the signal will pass. Now, you have theta I is equal to theta r, and then you are having theta, relations between theta I and theta t, right? And now this transmitted signal, basically if you are looking for a transmitted signal, then you take the signal. If you are not looking for the transmitted signal, obviously you have to put one more metal at the back side of the PCB, right? So in that case, obviously your field will become zero. So you are only playing with the reflected wave. So that point in time, your surface will become reflective surface. If you are not keeping any metal over here, that point in time, your surface would be transmittive surface. It means the output signal that you are looking from the surface has to be the transmitted wave. Followed by, what is the Fresnel's equations which is being followed? I guess all of you know about it. The reflections and the transmissions, it has to be like these always for a parallel polarization case, and for the perpendicular polarization case, the equation is a very standard electromagnetic wave equation that you all know. So this is the thing that we have been following. Followed by, what are the different varieties of FSA? There are multiple. These are, I am just placing some of the few, very few. Okay, there are many combinations. Now let me tell you the fact. You have, you can see Jerusalem claws, anchor shaped, and all these things. All these shapes will give you a very specific filtering applications. They are very, very specific filter. Obviously, if suppose, say for an example, if that Jerusalem cross that you can see, if it gives you the band pass response, if you make the complementary of this one, it will give you the band stop response. So this is the way that FSS plays. Nowadays, most of the FSS are basically combinations of two structures, or can be combinations of the three structures. That's where the novelty comes. Nowadays, if you are working on the PCB surface, PCB, printed circuit board, that point in time you have to think of your design in such a way that your structure has to be support multiple different, the novelty of the design will come whenever you are combining different varieties of structures together, such that you can propose a new structure. These are very conventional structure. These are the theory behind the FSS. Okay. Now, what are the characteristics? As I said, for a characteristics of the FSS, it has to follow the spatial filtering applications. It should have the frequency selectivity. It should have the polarization sensitivity. In addition, obviously, it should have the angular stability. Now, With these configurations, what are the types and classifications? How one can classify the FSS structure? Things are very straightforward. See, if you are making it as a some kind like a metallic grid manner, okay, this is like a metallic grid. So now these, first of all, the type of these FSS, they comes under two categories. One type is called non-resonant structure. One other type is called resonant structure. Things are very simple. Why? Because non-resonant means only one of the parameters will be available to you, either inductor or capacitor. If both the parameters are available, that point in time structure will resonate either in series or in parallel, because it is structure is getting L and C together. Non-resonant means either inductive or capacitive. How one can distinguish between these two? An inductive grid, wherever there is a metal, if you make it as a gap, like a complement to each other, that point in time it would become a capacitive structure, right? Now, what is the second category? Resonance structure, where I am going to apply both capacitor and inductor together. Now, how will you do that? Make the same square, but keep a gap between each and individual cell. That would become a band stop filter. Once you make the complementary of it, it will become the band pass filter. So, band pass is basically is something like this, where you need to have more metal to some extent. Okay, so that would give you the band pass response, and this is the band stop response. So this is the conventional, this is the concept behind the FSS. Okay, what is the conceptual part of the FSS? This is the conceptual part. Now, and these are your peripherals. These are your peripherals that you are going to use in your design. Obviously not the same thing, something you are going to make some changes that you are going to make on the structure, and you are going to place it on the surface to get the required amount of signal. Now, this is then whenever you are talking about the filter, okay, FSS as a filter, ultimately FSS will give you the filtering applications. Every time you know that in case of filter, we all concentrate on where are you getting the transmission zeros, where are you getting the transmission poles. Now, in some of the cases, intentionally you are adding some transmission zeros to your structure. Some of the cases you are adding transmission poles to the structure. When to add what? That is the question. Now, if you look at the geometry, if you are keeping the capacitive square patches, undoubtedly this will give you what? Either it would give you this capacitive structure, until and unless you are making a metallic ring on the periphery. See, what is the difference between these two? Here, what you can see, if you place a metallic ring along the periphery, it will again behave like a band pass, started behaving like a band pass filter. Now, question here is that if you look at this is the capacitive square patch, simple capacitor model. This is what is would be the response. This is going to be the response because a simple capacitor, whenever you are placing it, it would become a low pass response. When you are making an inductive grid, it would give you the high pass response. Whenever you are making the multiple arrays, it will give you something, some band stop response. And the fourth part is simple. Whenever you are making a array like this, it would give you the band pass response. Now, all these responses, if you look at it closely, now the filter response is basically depends on the presence of loss. Straightforward, because from the filter is a combination of what? Filter is a combination of resonator. Here, what are you doing? Suppose in your first in FSS designs, you are making the unit cell. Okay, so intentionally I am spending little more time on this because this part is more important to understand. This is the conceptual part. Whenever I'll be showing different designs to support this discussion. Okay, later on I'll be presenting some of our designs that is basically to support whatever I am telling it at present. Okay, so please pay your attention. This is the conceptual part of it. Now, when you are making a filter, not only FSS, for any conventional PCB substrate, first you are making the resonator. Whenever you are defining the resonator, that point in time, ideally speaking, what kind of response you want from a resonator? You want it to be like an impulse response, right? A very sharp peak. But when you are looking for a sharp peak, that point in time, what is important? Important is the quality factor. And now the quality factor is a function of what? Quality factor is a function of loss. One can always say the quality factor from the quality factor definition, it is energy 2 pi times of energy stored by energy lost per unit cycle, right? That is the quality factor definition. Now, whenever you are improving the, if you are improving the it is not always necessary that you have to improve the quality factor. Sometimes intentionally we deteriorate the quality factor. Why? Because whenever you are improving the quality factor, you are basically talking about the narrow band filter, right? When you are looking for a broadband filter, that point in time, you are basically increasing the loss intentionally to the surface such that you can get a broadband. Now the challenge is what? Challenge is to get a stable broadband. That is the question. How will you get a stable broadband? Suppose somebody is working from 1 to 6 gigahertz and you want a very flat S21 response on the filter. How will you get it? Now there is a design constraint over here. Now the question here is that whenever you are making it, whatever the, you can see that whatever the responses from third and fourth, okay, obviously you are not playing with first and second to some extent. You are most of the time you are playing with third and fourth. Now in third and fourth, suppose if I take an example of the third case, if you are making a simple metallic array like this, first what are you doing? You are basically designing the single resonator, right? You are basically designing the single resonator, then you are applying it on an EM simulator to simulate it with the help of a Flockett port. What Flockett port does? Flockett port will consider your array, whatever you are showing it one unit cell. Your Flockett port would consider infinite array towards x and y direction. I told you all these are 2D based FSS structure. So you are what are you doing towards the x, towards the y directions? It would consider infinite cross infinite array element and it would simulate based on that. So ultimately your job is to make your first unit cell as per your desired response. Important thing is what? Important thing is to know what is your inductor and what is your capacitor. Based on that, just by tuning that, you can get your desired frequency response, right? Now, how to control that desired response? Suppose, say, if you are making a band pass filter, you want a sharp stop band rejections at this point. How will you control that sharp stop band rejection? You have to control it with the help of transmission zeros or transmission poles. Okay. Now the question here is that what is transmission zeros? Now if you look at it, if you look at the S21, in an S21 response, if you are getting the sharp dip over here, this sharp dip, that dip point, whatever it is showing at 10 gigahertz, that is called the transmission zero. What is then transmission pole? You have to show it, you have to see to the upside. This one should give you the this is called transmission pole. Okay, so now, so what is the what are these two things? This transmission zeros is basically comes when you are talking about the band stop response, right? This is your S21. Okay, this is your S21. Now in the S21, what are you seeing it? In S21, whenever you are seeing the band stop response, you would consider most of the cases, we consider the 10 dB line. With respect to the 10 dB, what is the bandwidth? Okay, our bandwidth is close to 7 gigahertz till up to 12 gigahertz, right? That is the bandwidth. And where are you getting the transmission zeros? At 10. Similarly, if you look at the band pass response, you should consider the transmission pole. Now, where are you getting the transmission pole? Transmission pole should come at the maximum peak. Now, the question here is that is it all is it only restricted? Transmission pole is only, or transmission zero, is it only restricted to the bandstop filter? No, you can always do something on your structure such that you can get the transmission zero even to the bandpass filter. Okay, such that you can, suppose if there is a fly off over here, you can make the response to improve the sharp stop band rejection. I should apply the transmission zeros over here such that this guy will come down and it would give you the better performance. So most of the time inherently transmission zero comes in the band stop, transmission pole comes in the band pass response. Okay. Now with this, what are the different varieties of FSS? There are different varieties. Like FSS can be used in an antenna radome. FSS can be used as a reflector. Okay, you can see the reflect array antenna, right? You can see that. One can use the FSS as an antenna superstrate applications. One can use FSS as a circuit analog based absorber. One can also use FSS as a polarization converter. There are various applications of FSS. Okay, so this is the conceptual part of it. Now I'm slightly little to go little bit faster than previous. Okay, so now these are the conceptual things that one should know from on the FSS. So let me start with what is okay. Before that, one more important thing. Okay, what is I said angular stability. Okay, and another thing is called the grating lobe. What are these things? Now whenever you are making the FSS, miniaturizations of the FSS unit cell is required. Question is why it is required. Suppose if you are making FSS at a very high frequency, with respect to the wavelength, it is already miniaturized, right? So high frequency I meant by 60 gigahertz or maybe 40 gigahertz rather. Okay, your structure is miniaturized. Challenges will come if you are making the FSS, say for an example, at sub 6 gigahertz or maybe sub 10 gigahertz rather. That point in time, your wavelength will become same. So same in the sense wavelength will become very, very high on a higher side. That point in time, you have to do something to miniaturize the structure. Why? Because as I said, whenever you are doing the simulation, you are considering infinite cross infinite array, right? Now you have a response by considering the FSS with an infinite arrays that would give you the much more idealistic response. Now, from after the simulations, when you are giving it to a real shape, you are defining the array. Like maybe it is 10 by 10 or maybe it is 20 by 20 based on your fabrication capability. Correct? Now, when you are doing all such things, obviously speaking, within a given area, your aim should be accommodate more number of unit cell such that you can go close to your idealistic response like infinite cross infinite. Obviously, infinite array you cannot make practically. It means higher number of arrays. Suppose if I give you, somebody has to design an FSS surface, I can only accommodate 20 centimeter by 20 centimeter area. Now you have to make your surface within that area only. That point in, and I want as many as array as possible without compromising the given specification. Okay, suppose I want my transmission zero. Suppose you are making a band stop FSS. I want my transmission zero at 3 gigahertz. Okay, so that point in time, your aim is what? Your aim is to miniaturize the structure and accommodate more number of unit cell. This is the problem statement. So try to design miniaturized version of the FSS such that you can accommodate more number of unit cell within a given area. Why it is important? It is important because suppose if you are looking at the angle, suppose this is the total length of the FSS that is defined by D, and it is having n number of structure that is multiplied by PC, that is the phase shift. So now if you consider that, then your structure, when the signal is coming, what is happening? As you all know from the antenna array perspective, this is basically, suppose the angle is falling under the theta, then your phase of this signal is nothing but sorry, the PC is called the periodicity. So now your, what is the phase shift phi? It is called, it is basically k t sine theta. What is sine theta? What is theta? Incident angle. Now how are you calculating this phi? There is a given formulas. All these are very taken from the textbook. Omega by c, this d multiplied by sine theta. Okay, that is nothing but kd sine theta. What is k? To omega by c. Okay, And what is k means, beta, right? I mean, k is nothing but the wave vector, that is beta. Okay, so now how do you define the phase velocity? Omega by beta. So that is nothing but like this. Okay, so if you write omega by uh, velocity, that is nothing but your beta multiplied by d is npc, and sine theta, that is called what? The maximum phase shift that you are getting at oblique angle. Now, when you are talking about the angular stability with respect to these oblique incidents, that point in time, you are going to face something like a grating low frequency, because these grating low frequencies also depending on, surprisingly, on this n, on the periodicity, on the sine theta. Okay. Now, it may so happen that at some number of array, you are getting some kind of another higher strength signal. Okay, like in antenna array, you got another maximum lobe close to the main lobe. That lobe, that maximum lobe, that you are getting close to the main lobe, which is unwanted. But it will come. Your job is to shift that lobe up to a reasonable distance. Question here is that you what you need, you have to delay that grating lobe. It means it should come much later, and also larger number of unit cell can be placed within the fixed area, as I said. And what are the techniques of doing it to overcome this grating lobe and to miniaturize the structure? You can use lumped reactive loading, you can use convoluted geometry, you can use fractal geometry on a single layer, and on a multi-layer, you can make the structure as 2.5D of FSS, and you can use some kind of a capacitive grid-based structure. So, capacitive grid means what? When you have a more metal on the structure. Okay, it is just complementary to the inductive grids. Okay, so this is the way one can improve the miniaturizations on the FSS and also to overcome the grating lobe of the structure. Now, question here is that there are different varieties of miniaturized FSS are available. These are the some of the structures you can see. This is the lumped reactive element, convoluted geometry, and other thing. Now, with this, let me start with the experimental setup. Many of you have some kind of a confusions how to test the FSS, what is the requirement that one need to get the FSS struggle, the response. Think here is as follows. If you are, either you can do this kind of measurement within the anechoic chamber or outside the anechoic chamber. I always recommend FSS to be measured outside the anechoic chamber, because ultimately when if in a practical scenario, whenever you are testing the FSS, you it is not possible to give the anechoic chamber, right? So right from the beginning, let us try to test the anechoic chamber, sorry, test the FSS within, outside the anechoic chamber itself. Now, what you have a transmitting horn, you have a receiving horn. In between, you are making the FSS. This structure with respect to when you are playing the FSS in a transmittive mode. So, receiver and transmitting antenna is transmitting the signal, and whatever the signal is transmitted from the FSS, you are capturing that signal with the horn antenna. This structure with respect to the transmittive type. Now you can see the similar responses inside our anechoic chamber, whatever the schematic you can see. Now this is the call of the this is the sort of a measurement which is basically the reflective surface. Now, what are you seeing? This is the transmitting horn, this is the receiving horn. In between these two horns, you are placing some kind of an absorbing sheet such that they are mutually decoupled, these two antennas, and you are testing the surface. So, now the distance between the horn and the FSS has to be made on over the far field, 2d square by lambda or lambda by 6, whatever the way you want to consider. Then the edge of the FSS are covered with the aluminum foil that you can see it because of these. And then also the absorbers are placed to avoid the diffractions of the wave that I have mentioned over here. So this is the conventional experimental setup that you are going to adapt. With this, let us start our discussions. I think you have some kind of an basic overview, basic understanding about the FSS. Now let us try to go into some kind of advanced model of the FSS. I'll directly start with the multiband FSS. How to make these multiband FSS? The way we have made a structure like this. You can see this structure is basically like it is more like a close to a Jerusalem, but some kind of a changes has been made on this structure. And in that case, the as I see this, the ports have been defined, and then these FSS, how this design has come, that is important. If somebody today, if you are trying to make similar kind of a structure like this, how to come to this structure, rather than directly seeing this structure, you should know how we have achieved this idea. That is important, right? So now how we achieved it? First of all, this, we are trying to get the FSS with a capacitive grid, and we have taken the substrate as RTD rod. Now we are playing with a cross, where you can see this is that wherever there is a white screen, sorry, wherever there is a white, there is no metal. Blue is metal. Okay. Now after that, we are making a arrow type of things to add more capacitor to it. Then we are playing with the structure, gives more inductor. Clear? Step by step process. First, you have to add capacitor, little more capacitor. Whenever you are applying little more capacitor, there are some inductor which is coming from here, from this metal, from the violet color things. White is always gap. Okay. From the violet, you are getting some little amount of inductor. Give more inductor, you have to make more lines to it. That is the way. And why you are making it like this? To make the structure as compact as possible. Okay. Now after that, we are seeing, if you see it, this is basically like a multiband FSS, which is, you can see that this is your S11 response and this is your S21 response. Obviously speaking, looking to the transmission coefficient and looking the response like this is your transmission poles, right? And this is your transmission zeros. Okay. So now this is basically comes here, how many transmission poles you are having. You are having basically like from this structure, if you look at the red color graph, it is basically showing you two transmission poles. And how many transmission zeros you are getting? Two transmission zeros. Okay. So now this is the FSS structure that you can see. Now coming to that fact, next part, one more thing is important over here. Whenever you are making it, if you look at the unit cell structure, it is very less, and the periodicity, it means PC, as I said, you know, right? PC is also the functions of the grating lobe, and this is nothing but some zero point 0.1 times of lambda. Okay. It is basically having high selectivity and good angular stability of 55 degree. You know all the concept of angular stability I have already mentioned. Now the question here is that next part we are going to test the angular stability. You know how to test it, as I showed you the surface, and you know why it is important. Now this is for the TE mode. You can see this structure almost satisfying up to 40 degree. This is TM mode. It is also satisfying up to 40 degree. Beyond 40 degree, things are deteriorated. Then from here, what you can see, it is a single band structure, isn't it? It is only resonating close to 6 gigahertz. Now, let us see how to transform this structure from single band to dual band. For that, this is the structure that I had shown, and we are basically making it an array. And over here, we are giving one more slot like this. You can see that we just rotate the structure. Okay. Just after that, see, you can see that there is another slot which is coming when you are combining this structure. Now if you look at it holistically, when you are making four cells together, it's very interesting, isn't it? When you are making the four cells together, at the center you can see something like a Jerusalem, right? You can see the blue shaded thing. Now with this, it is becoming the dual band, and now we can see the dual band response of this. Okay. Now with this is the 3 dB bandwidth, stop band resonance, and everything that is present over here. Okay. I'm not going to the details of the desired, the obtained performances. One can always refer to our paper and other thing. Okay. I'll show you that too. Now After that, you have to vary the parameters and to optimize it. The parameters is this, basically the functions of your own design. Then again, you have to you have to make the T and TM mode, and after that you are getting the performances. And what is the relations of the quality factor over here? I say the quality factor also plays a role. For the band pass filter, this is the quality factor definition. For the band stop, this is the quality factor definitions. Okay. Now let me begin with the tri-band with a similar structure. If you are making it as a conformal, now you can see this is the conformal. Okay, we have made it on a very thin substrate, 0.25 RTD. You can see on the 0.25 RTD. You can see you can fold the structure, and finally you can see the you have to see the equivalent circuit model. You can look at the equivalent circuit model. All everywhere there is a inductor, and there whenever there is a gap there is a capacitor. Okay, and now this is for the outer ring. You have two rings, right? If you closely look at the structure with respect to my this green color, you have two models. One model is this. Inside you have one more model. Now why these inside models are being placed? To make the structure more compact and to get more inductor and more capacitor out of this structure. Okay, so then it is being placed over here and it has become the final structure like this. Okay, now question here is that how will you calculate this inductor and capacitor? That question always comes to your mind, right? How to calculate these values of inductor? I get an inductor, how to calculate it? So now how to calculate this inductor and capacitor for a physical dimension? What you have to do, as you all know, if you have a metal strip, it has a value of L. Whenever you have two metal with a two different length separated by a distance, that could be one case. Third case would be two metals, they are basically not they are having overlap, some overlap. Okay, here we are not considering the overlap, only the gap. You can extend this line till up to this point also. Okay, but in one case there is some overlap. These could be the three cases. With respect to these three cases, you always have some kinds. With respect to the metal, you always have some kind of a self inductance. Effective inductance in the presence of mutual inductance means what? This, or with respect to this diagram, this, that is the effective inductance. Then from the case one, what is how to calculate the mutual coupling between L and M? That is the formula. What is the mutual coupling between the second case with respect to this overlap? So now what is the, okay, I forgot to mention one thing over here. Most of the cases, what you can see that this, you have to calculate this overlap, and you have to keep, I guess all of you know that, you have to use the same unit across everywhere. If you are considering the centimeter, or I always suggest consider it in millimeter for a unit cell. So now if you consider in terms of millimeter, this is all the dimension has to be in millimeter form. Okay, now from there you can calculate if you have a gap something like this, you can use this formula to calculate the capacitor. Okay, so this is the way I am just moving it further beyond. So this is the way one can see the performance of this FSS unit cell. Now if combining all these models and everything, if you combine all the unit cell together, look at the equivalency. Making the equivalent circuit model is very, very, very important. Yes, I am intentionally emphasizing this very, very part of it. Okay, because why it is so important? The reason is that this equivalent circuit model will give you the inline story or some what is exactly happening to your structure. Without that, you won't be able to, suppose today if you are making it, tomorrow somebody asks you, okay, you are getting tri-band FSS at 3, 5 and 7 gigahertz, can you make it at 10, 15 and 20 gigahertz? Then you should do it in a one day time. If you really know your equivalent circuit model of it, you just need to change the equivalent circuit model parameter, simultaneously make your structure in that way, and your structure will be ready. Okay, so each and everywhere this inductor capacity, everything, it has to be the function of your structure. Okay, now analytical calculations of S11. what you have to do first, you have to find out the impedance of the FSS or YFSS, admittance of the FSS. Then you have to do it in a conventional ABCD matrix. Okay. Then you have to calculate your S11 and S21 using the conventional formulas. All these formulas are available. And then accordingly, you can see HFSS model, circuit model, and analytical model. These three things we are showing it over here. All these things, whatever we are discussing, you can get it in our paper on IEEE transactions in electromagnetic compatibility. All the details, including these equations and other things. Okay. So now what you can see it's a tri-band FSS where everything is almost matching to some extent. Okay. So this is S11 and S21. So this is the flow of the structure. Okay. Now if you calculate the transmission zeros of it, now your transmission zeros are basically comes. You have to see come to your S21, see where is the dip. Dip is over here. So your transmission zero is at 4, 6 point, close to at 7, close to at 11.3, something like that. So these are your frequencies. Okay. Now with this, then you have to see the filter response at normal surface. What is this all about? It's basically like you have to see the filter response in terms of, you can see you are getting the filter response like this as it is a triple band filter. Okay, this is for with respect to the oblique incident response. Then you have to see it with the sorry, this is the normal surface, normal response, normal incidence. This is the oblique incidence, where you can see this structure can support experimentally up to 60 gigahertz. Okay. So, oh, okay. So what you are looking to the y-axis, AC. AC is called shielding effectiveness. Okay. So we have to see shielding effectiveness should be maximum in terms of dB at your desired transmission zeros, right? 4, 7, and 11, wherever you're getting. You can see there is a slight deviations with respect to the measures and the simulation response. Okay. So this is all about normal incidence and oblique incidence case. Then whenever you are making the conformal FSS, right? Now in the conformal FSS, you are making the structure conformal like this, and you are taking the unit cells from here. Okay. And once you are taking the unit cell from here, what are you seeing it over here? You can see that this unit cell is basically like all the structure has to be conformal with respect to these angular incidents. Like you can see that with respect to the critical angle. What are the keywords? So this part is very important because normal FSS surface won't have more, some has some applications, but whenever you are making the conformal FSS, it's basically your applications most of the time is in the radome applications, right? So now it has to be so inside the radome you have the antenna, correct? So most of the cases your structure has to be, to some extent, has to be transmittive at some frequency and reflective to some other frequency. So this is the response when you are making the structure as conformal. This is the response with respect to the shielding effectiveness. And with respect to this RC means from the center. If you consider the center, you can see it over here. What would be the radius? What radius you are considering? One time you consider 43.6 mm, one time you consider 52 mm. So this is all about this. Then after that, we thought of again, let us miniaturize the structure one more time. Okay, it is called ultra miniaturized FSS. What are you doing it over here? A structure has been changed like this. You can see there are two layers FSS. It is also called the higher order FSS. What are you doing it over here? You make one surface like this, you make another surface like this on the back side. Both are metal, red and blue, both are metal, and they are both the structures are combined with each other. In back side, sorry, in between you have the dielectric. That is all about. Beauty of this design is what? It is a single layer structure. It is a single, you are not using two PCBs. One PCBs, you are doing the everything. Now, in this surface, what you are doing it to, now these two FSS are basically, they are connected with some metal vias. Two FSS layers are connected using the metal vias. Where are these vias? How many vias are being used over here? let me tell you, there are four vias. One is, you can see the green color. These green colors are vias 1, 2, 3, and 4. You can see a dot over here, right? So these dots, this white dot and these yellow dots, both are connected together. So now it is basically providing the current path to it, okay? And this structure, as you can see, it is comes under the cross dipole category. So now what you can see the shielding effectiveness from the triple band. This is also a triple band, but it is much more miniaturized version of it. And you can see it is up to 60 degree. It has the shielding effectiveness, and you can see the first band, second band, and third band bandwidth. Everything is falling under the sub 6 gigahertz and has the potential applications. Okay, you can see in most of the Indian scenario, ISM bands in Indian scenario, it comes under close to 860 megahertz, which is 0.86. Here I forgot to mention, it is comes under 0.847, close to 0.860. Okay, so this is basically comes under the ISM band. To some extent, this is slightly shifted. It is around 1.5 ISM band. This is also 2.4. Okay, so these all has some kind of a potential benefits in terms of the application scenario. Okay, now with this, I'm just keeping these slides for with the interest of time. So now I'll just quickly go to the applications of the FSS with respect to the antenna. That would be much more appropriate. So I think you have some understanding about it. Now let me show you the applications. With interest of time, I am just going to the uh, okay, multifunctional FSS. Okay, because my session is on the multifunctional. Now, whatever the concept you learned so far, you know the all the basic topologies of FSS. You know what are the things that you one should concentrate or consider during your design for making an FSS structure, like it should obey the grating low performance. Your structure should be miniaturized, and then finally you have seen that from one structure how to go from one band to the second band to the third band. Now the question here is come, is it so one project has come to us, I want a single FSS cell or single FSS geometry that can act as an absorber, or that can act as a polarization converter, or as well as that can act as a spatial filter. So, coordinator, how much time I left? Could you please tell me?
Sir, we have session till 12:30, sir.
Okay, fantastic. Okay, so I have still half an hour. Good, I can spend some time on this now. So now here the question here is that how to get these multifunctional FSS. Now, first of all, whenever you are making the multifunctional FSS, we experience a problem like it is sometimes it is difficult to make it as a conventional 2D structure. Rather, we thought of, okay, we will consider X, Y, and Z directions also. So now we have seen our structure with X and Y. Now we are increasing the Z directions of the structure and trying to take Z directions effectively in the design. It means the Z axis, we are now going to emphasize more. Okay. Now, how are you going to do it? Obviously, red color is one metal, blue color is one metal. Z axis is gives you these vias, metal vias. So this is the called of the 2.5D FSS structure. Now, in this case, what are you seeing it? First of all, whatever I'm presenting, all are my PhD students' works. This work is accepted in, you can get it in IEEE transactions on antenna propagations. Okay. Now, this is the structure, that top layer and the bottom layer. You can see it over here, and all the structure geometries and everything, they are basically optimized, and then followed by it. These are the unit cell dimensions. Look at the unit cell dimensions, very, very low, and these structures are basically considered with the help of Jerusalem cross, and I connected the meander square loop structure. There is a reason for it. What is the reason? Reason is comes with the equivalent circuit model. Now I am presenting the equivalent circuit model to you. Now see that thing, how we have designed it. First of all, whenever you are making the structure, you should see the structure from the top, from here. Don't see it from here, not from the side. You have to see from the top. Why? Because you are playing with the structure with respect to the air impedance. free space impedance. Okay, your Z naught is not 50 ohm, your Z naught is 377 ohm. After that, with respect to this structure, this, okay, the top layer, this is the corresponding equivalent circuit model of it. After that, with respect to the bottom layer, you have this. In between, you have this. What is this? This is nothing but your dielectric layer, because signal is going to the dielectric layer. This HS is the length of your transmission line. Okay, that you can see it over here. Okay, that is HS. Now, all these things are basically the function of the kind of inductor and capacitor you are considering in your structure. Okay, so this is the way you have to come to the equivalent circuit model. Now, corresponding to that, then we have considered the circuit model and HFSS. Both we are comparing whether we are getting the required amount of response or not, both are matching or not. Okay, so this is the S parameter response, S11 and S21. Just by looking to the structure, one can see that this is basically what is basically like, you can see at the uh, blue color thing, S21. S21 is going down. It means what? S21 is going down means it has to be band stop structure, right? And S1 is going up means it has to be the sorry, for that reason your S11 is going up. Now what you can see, if you look at very closely over here, if you can see that here you are applying, wherever you are getting the band stop, as I said, you are getting the transmission zeros. Now, in between two transmission zeros, you have a transmission pole. It means in between this frequency, it acting as a band pass response, right? It will always happen, but you should model the structure in such a way that you can consider the band pass as well as band stop. Look at the response, which is in case of band stop, band pass, it is very close to zero, right? So now it's basically you can call it as a dual band pass and band stop response, or else you can call it as dual band filter, dual band pass and band stop filters. Okay, so this is the S parameter response. For you can see that, but this is the performance. Insertion loss is very less, 0.6 dB. Okay, now with that, let us see the, with respect to the first, you have to see with respect to the transmission zeros, where are you getting transmission zero? In some 2 point something, and and at close to at 4. Now what you should know, which part of your structure is responsible to get this response. You should not take it blindly that okay, I am getting transmission zero at this frequency. Which part of your structure is helping you to get it? Similarly for transmission zero, similarly for transmission pole, right? So now with that thing will help your surface current propagations, will help you to do that. Okay, so this will also help you to model your equivalent circuit model also. Now you can see that the transmission zeros and transmission poles at both the two frequencies. Now which part of the structure, you can see that over here, you can see the at this point all these lines are having less evident in terms of this. Now, only the difference between two frequencies over here, okay, is this line, the vertical line. If you look at it very closely, basically like with respect to these and these bends. Now, what you can see it in this case, this line is more effective. You can look at the color profile, right? So over here you can see this line is not much effective, but side lines are to some very effective. So basically like it seems to be like that your these and this region are helping you to get response at 2.3. Over here on your structure, your these all these bends means more inductor, are helping you to get what? Gate of next transmission zeros. After that, structure is being fabricated. This you can see, this is the front side view and the back side view of the structure. And then it is its angular stability performance. It can, we see it can go up to 70 degree, okay, for both TE and TM. Okay, it is the more angular stability. However, on 70 degree, slightly some distortion has come, but it is tolerable limit. Okay, as much your this part is not moving below 15 dB, you can consider, or maybe 10 dB to some extent. Okay, now this is the performance of this. Then the similar structure, if you do some modifications on it, what are the modifications that you are going to do? Some on the keeping the same structure, you are adding something like some FR4 substrate with some kind of a ground plane and with some ring. Okay, some backside ground plane and some ring. This will become an absorber. Same structure. Okay, now you are increasing the height of the substrate, or I would rather call it as a the transmission line length. Then making some changes on the other layer. Okay, and then finally it would give you some kind of an absorber with a triple band. It should give the same triple band phenomena, but some changes has been made on the design. Some additional periphery needs to be added to get this response, because structure has to be very lossy in when you are talking about the absorber. Okay, then this absorber, obviously it has to be checked with absorbability. You can see at triple band you are getting the triple band and quad band, both you are getting. So now you can see for the quad band you are getting much more absorption peak is close to again 4. So it's basically like at 100, almost 100% absorptions we got. And then we have changed, see the, as you know, the phase has to be 0 where you are getting 100% absorptions, and your magnitude real part has to be has to go to the close to 377 ohm or something like that. So all these things needs to be checked in terms of the medium parameters. Okay, so now then we'll be concluding our discussions, showing some of the applications of the FSS for antenna applications, considering the current 5G and 6G scenario. Now, what you can see, this is one of the FSS structures made on tectonic substrate, which is having a ground plane. Then the structure has been fabricated as an FSS array. Then structures have been tested using an waveguide method here, because we thought of testing it with an waveguide. Either you can use the horn antenna or you can use the waveguide to test it. Okay, that is also possible. Here in this case, we used waveguide. Two rectangular waveguide in between this FSS has been placed, and then this FSS is basically, it has the also the quality of the electromagnetic bandgap structure. So we have seen the dispersion profile where you can see its operating regime. We are using it from close to 7 to 12, whether it is getting it or not, between the first mode and the second mode with respect to the light line. If you see, you can see the band gap is like this. Then we have seen the S11 performances, S parameters. So it's basically it's not S11, S parameter performances with respect to S11 and S21. It is almost giving the filtering response. Then what you have done, we have made these, keep the FSS on top. Then we make one antenna element over here, and on the back side we use a capacitive grid, or you can call it RIS. This is not a reflective intelligence surface, no. Okay, this RIS is something different. It is called reactive impedance surface. Reactive impedance surface. Reactive means you're only playing with either inductor or capacitor. Okay, it is nothing but a high impedance surface. Okay, reactive impedance surface. Now what we are doing it, the reason is that antenna is a simple patch antenna. Now, no point in discussing on the antenna part over here. The discussion point here is that what is the purpose of adding the bottom layer and the top layer. First of all, top layer is, you can see the placement of the top layer. Obviously in the back side there is no metal. This layer is over here. This layer is basically helping us to get whatever the signal it is coming after reflection of the signal, everything is going towards making as a constructive interference. What it is, the antenna is radiating, then the surface, there is a reflections, multiple reflections is happening, and then there are reactive impedance surface over here that is helping you not to leak the signal to the backside. All the signal it is throwing to the upside. Okay, now basically like it is playing as a ping pong ball. It's like continuously coming, dropping, and again going up, dropping and again going up. Like that, multiple responses are coming, and all the responses are basically uh, summing up together to get it as a constructive interference. So this is basically called partially reflecting surface acting as an FSS. Okay, you can see it over here, and this phenomena, whatever I have said, the technical term of this phenomena is called Fabry-Perot cavity. Okay, because here you are making a cavity, and when you are making the cavity height is important. Now you can see this is the response of S11 over here. You can see that the simulated and measured return loss of these antennas. You can see this antenna is close to a broadband antennas. It is basically coming from close to at 10 or some 10 point something to till up to something up to 12 gigahertz. Now look at the beauty of the structure. We have seen it in a multiple combinations. You can see without superstrate, with superstrate. Okay, without superstrate measure. Now here dual EBG superstrate, it means what? The red color. You can see the red color thing, which is exactly gives you the better performance compared to the other. Okay, now coming to the fact of the final structure. This is the fabricated structure finally. Okay, we have used the metallic screw and other thing to get it as a conformal shape and other thing. Then that structure is being placed inside the anechoic chamber to test it, and then finally we check the gain with respect to different varieties. Now you can see the gain has been improved a lot. Now the antenna, forget about to get a gain like this close to 14 dB or 15 dB, whatever, from a single patch. Now here there is no novelty on the antenna design, but there are something on the other side of the story, like on the peripheral. You are adding more peripherals to the design to improve the performance. When you do not have any constraint in terms of the size, this concept cannot be blindly adapted everywhere. This concept you can only use if you are using these kind of antennas for military and space applications. Okay, this is the corresponding E plane and H plane patterns of it at 10.8 gigahertz, which is being shown over here. Now, after that, we have also checked the concept with antenna array. Here I showed single antenna. If I make the similar antenna arrays over here with the similar kind of atmosphere, similar kind of arrangement, we have, this is just for our sake of interest, we have done it. What will happen if I increase one element to the four element? Okay, this is the four element corporate feed antennas. So now what you can see it over here, the gain has been improved a lot. Okay, and almost like this. Okay, this is again without superstrate and with EBG. Okay, this is the gain of this antenna and antenna array. Then other applications of the FSS can be used to make it a reflect array antenna. Very interesting. Take a simple horn antenna, in front of the horn antenna you place the FSS. Look at the placement of the FSS. Okay, you place the FSS, then what is happening? Your signal is going and signal is reflected. All the reflected signal should be in phase to justify its operational principle. And after that, look at the performance of it. This is the single horn antenna reflection coefficient. Obviously, whenever you are adding it on this, say for an example, the you are getting much more distortions, but everything be below 15 dB, close to on simulation. Okay, you can see that this is the response. Now look at the gain. Okay, now the gain is what? The gain is basically uh, the Okay, what are the different D's? These D's are the aperture. Okay, multiple different apertures are being sorry. D is the distance. Sorry, I beg your pardon. D is the distance in millimeter. One case we consider 72, 75, 78 because you have to optimize the D, right? Such that you can get all the signals in phase. Now, after that we check the gain. Gain, you can see the gain has been improved a lot. See, this is the conventional horn, and this is the measure. The after adding the FSS, improve the gain up to 22 dB. Look at the response of the gain, normalized gain response with respect to theta. See, horn case and black one, and when you are adding it, okay, you can see this is the co-pole and this is the cross-pole. Cross-pole, you can see very less co to cross-pole ratio is very high, and see how the directivity has been improved. Okay, so this is for the E plane. Similar kind of responses have been observed in the H plane also. The signal is very sharp and no more grating lobes are present up to 120 degree. Okay, so this is the another ways one can use. There are many ways, actually many applications one can think of adding the FSS structures. Okay, I'm just showing two. FSS can be used to improve the mutual coupling reductions in an antenna array system. FSS can be used to improve the portable communications, portable antennas, okay, to improve the performance on a portable antennas like tablet, mobile phones, and other things. So these are the different varieties of applications that are available. So now with this, I am concluding my discussions today. So these are some of our papers where I have taken it. All whatever the work I have presented, everything is in our work, and their corresponding references are present for your quick reference. Okay, or you can see those references and you can read those papers for more understanding. Now, let me thank Department of ECE, MNIT Jaipur for giving me this opportunity. And as a conclusions of my discussion today, let me give you a brief overview. What we discussed in this webinar, we started our discussion, we spent a quality amount of time on explaining what is FSS, what are the different varieties of FSS, and how to model the FSS, how to calculate the equivalent circuit model of the FSS, and also how to design the FSS starting from the single band FSS design, dual band to the triple band. Then we discussed about what are the design challenges of the FSS considering the current state of the art, like to miniaturize the structure, to improve the grating lobe. Whenever you are miniaturizing the structure, what are the challenges that you are facing, how to mitigate such effects, those are coming to your designs, from your designs, how to improve those parameters with the help of equivalent circuit model, with the help of an EM simulator. And also then I presented a multifunctional FSS where I had seen FSS can be used as a spatial filter as well as FSS can be used as an absorber. After that, I gave two applications of the FSS. One applications we discussed about at fabricated cavity antennas, which will basically improve the gain and or the directivity of the antenna system. Followed by I also discussed about using the FSS, how to design our reflect array antennas. These are the two applications we covered. And with this, I would like to thank Dr. Sarthak and Dr. Reena Kumari for giving me this opportunity, share some of my thoughts and deeds with you. And thanks for the opportunity. And wholeheartedly, I would like to thank IEEE SBC MNIT Jaipur also for giving me this opportunity. So thank you. The floor is open for discussion.
Thank you, sir.
Yes,
So, can we ask the question, sir, on behalf of the participants?
yes, obviously.
Okay, sir. Sir, one question is from my side only. Actually,
Hmm.
sir, I am designing a wideband terahertz antenna. And
Wideband terahertz antenna. Okay.
yes, sir. And
Hmm.
sir, I want to increase the gain for which I am using a antenna superstrate method using FSS.
Mm-hmm.
Sir, my question is that, sir, how would I decide the gap between the unit cell and the number of unit cell? How much should I take, sir?
See, do you really want to? Why, first of all, why you want to have a gap between two unit cells?
Sir,
See,
like I have seen papers.
see, if you look at, just a second, see, if you look at that is some of the things that is important. Now,
Yes,
come to the very basic understanding of the FSS.
yes.
Here, what is your unit cell?
Sir,
Suppose
that
if
I,
you, sorry,
yes, sir. Please continue, sir.
no, tell me, what is the doubt? I mean,
Sir,
you're saying,
doubt is that I am designing for increasing the gain, sir. Now
yeah,
I
I
have
can,
how to
yeah,
decide, sir, what should be my approach.
yes, yes. See, first of all, you want to increase the gain, so you want to make your FSS as uh, either as a transmittive FSS or as a reflective FSS, right?
Yes, sir.
If you consider it as a transmittive FSS, right, then what you have to do, see, here the gap of this FSS, suppose what is your unit cell here? This is the unit cell. Can you see my cursor over here?
Yes, sir.
Yeah. So this is the your unit cell, correct? Now, the gap that you are keeping between two layers, this is just because of the additional capacitance that you or additional inductance that you are getting from the structure. Or else, if you look at this, a very simplistic model, suppose this is your unit cell, right? This structure is basically giving you an inductor and the gap is basically giving you the capacitor. Now, the spacing between two arrays is predominantly, it is the function of the kind of capacitance that you need for to arrest your frequency. Suppose you are working at 1 terahertz. Okay. Now at 1 terahertz level, I don't know your design. Suppose I am assuming your design is just like a square box, square ring, sorry. Okay. Now in the square ring, you can always calculate the inductor and you precisely select the capacitor based on the gap between these two lines such that you can get an LC model. And that LC will give you the resonance at 1 terahertz. And then you subsequently follow the same array overall throughout the structure.
Okay, sir.
There is in FSS design, there is no any thumb rule or any specific formulas what would be the spacing between two elements. No, it is not an antenna array. Okay, it is
Yes,
basically you should treat the FSS in terms of periodicity, that is PC, in the way I defined. Okay, in FSS, it's basically now how would I call it one? Uh, how would I call this unit cell? One unit cell of this structure. My one unit cell is basically taking this. Then my line will go. My cut will go exactly center of these two array, like this and like this. Are you understanding what I'm saying?
yes, sir. Yes, sir.
Huh?
I'm
This is
understanding, sir.
very
Yes, sir.
important. Thanks for asking this question. So I'm requesting all the participants, please consider, suppose whatever I'm drawing, so this is my array. Now, what is, suppose this, if I draw a line, okay, this is my one unit cell, okay.
Yes, sir.
What is your name?
Swati.
Sorry, Shwati. So this is your unit cell, Shwati, okay.
Yes.
Now you tell me, what is there any spacing between two unit cell?
No, sir.
No, right? It
Yes,
is
sir.
FSS surface is basically, it is a basically taking all the surface together. All of them are attached together.
Got it, sir.
Okay.
Yes.
Similarly, here also, you can see this ring is much more thinner than this ring, right?
Yes.
Because here two rings are connected together, right? So
Hmm.
two structures, two units are attached. Have I made you clear?
Yes, sir. Got it, sir.
Yes. Thank you.
Thank you very much, sir.
Most
Sir,
welcome.
one question from the participant.
Hmm.
In slide number 22, how you calculated SC in dB in CST? Can you please explain this with the formula? Slide number 22.
Let me go to that slide. Slide number 22.
22.
Just a second. Hmm. Huh. This is the slide that you are referring to, right? This is slide number 22.
Participant, you can unmute yourself to ask the question directly.
Yes. What is the question? Yeah, tell me. So this is slide number 22. What is the question?
How you calculate shielding effect SC in dB in CST?
Oh, okay. No, 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 no. See, the CST, forget about CST. The calculations of AC is identical whether you are using CST, HFSS, measurement, everywhere. Okay. So there is a specific formulas are available. Okay. So you are asking me the formula, right? Okay. You
Yes,
can
sir.
quick. Hello.
Yes, sir. Good afternoon, sir.
Good afternoon. Are you asking me the formula?
Yes, sir.
Yeah. So please, I am requesting you to refer this paper. Okay. So there we have given the formula in this paper. It is available. If you are not getting this paper, just send me an email. I will send it to you. Okay. There is a dedicated formulas is available to calculate the shielding effectiveness.
But sir, when you are calculating the shielding effectiveness,
Hmm?
whether it is calculated using S11 only or S21 or both the terms are using for this calculation.
It depends. It depends on basically like what kind of FSS surface you are using. See,
Sir,
you the sorry.
sir, I am asking about absorber type of FSS.
Yes. Absorb. See, the point here is that in case of when you are doing the absorber, is it very necessary to calculate the shielding effectiveness?
No, it is not compulsory.
Correct. In absorber, you only concentrate on the absorbivity of the absorber.
Yes.
Okay. Now, shielding effectiveness is important when you are considering the FSS as a spatial filtering. Now, shielding effectiveness formulas are changed if you are considering the FSS as a transmittive FSS or you are considering FSS as a reflecting FSS. Now, if you are using a transmittive FSS, whether that FSS is a band pass FSS or band stop FSS, okay, based on that the formulas are there will be changed. I don't remember the formulas, but formulas are changing with that thing. Okay, so you can refer that paper to get the kind of formula that we used to calculate the shielding effectiveness. The direct answer to your question is that there is no one formulas for shielding effectiveness. It is basically depending on the characteristics of the FSS. It primarily depending on the characteristics of the FSS. If the FSS is, suppose if you are using the transmittive FSS, look at it whether it is a band pass or band stop. Why it is like that? Because in the band pass, hello, am
Yes,
I
sir. Yes,
audible
sir.
to you? Yeah.
Yes, sir.
In the
You are.
yeah. Okay. In the band stop response, you are considering what? Transmission zeros, right?
Yes,
So
sir.
you have to use that thing for your calculations. Now, giving you an example, look at this structure. Where are you getting it? At 4, right?
Yes, sir.
Maybe at close to at somewhere at 7, maybe,
Hmm.
right?
Yes.
Now, if you look at it, if you look at the this, where are you getting exactly at 4? Exactly at 7, right?
Yes, sir.
What is this? This is your S21. But what is this actually? It is a band stop. So it is your transmission 0. You are not considering transmission pole, right? Your shielding effectiveness is not coming at this frequency, right? Please try to
Yes, sir. Yes.
understand. This is a very conceptual point, okay? I am not showing your shielding effectiveness. Once again, I'm showing it to you. My shielding effectiveness is coming over here, not comes over here and here. Okay,
Yes, sir.
it is considering here. So what are you considering? You are basically considering the transmission zeros of the structure.
Okay.
Based on that, this shielding effectiveness has been calculated. Have I answered your question?
Yes, sir. Sir,
Yes.
I have one
Hmm.
paper.
Please tell me. Hmm.
I have one paper in which
Hmm.
absorption by using the absorber, it is
Mm-hmm.
showing the shielding effectiveness results and their
Hmm.
equations as well.
You
Can I
can
show
always
you?
show. Can I? Sorry, I missed last part of your query. What was that?
Can I show you that paper, sir?
Now?
Yes,
Okay.
sir. That
You can.
equation.
See, okay, you can share, but let me then take it in the end, okay? If other participants have any question, because I have to unshare my screen in that case,
Okay, sir. Okay, okay,
okay?
okay. Okay, sir.
So, yeah, you can always show me that paper, no issue. Do you have any other question?
No, sir.
Okay, okay, okay. Any other question from the participants?
Participants, you can ask the questions. So, like mathematically, we say that compact antennas are those antennas or design which have size less than lambda by 10.
Compact antenna.
Any like compact design, we say that the
Ah,
size should be less than lambda by 10, then we can say that it is compact. For ultra miniaturization, sir, that you mentioned the
hmm,
word
hmm.
ultra miniaturization, is there any numerical representation for it also?
No, 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 no. There should not.
Okay.
There is no numerical representations of it. It is straightforward. See the. Just a second. The ultra miniaturized by meant by. Let me open that slide. Just a second. This is, you can see, this is the miniaturized conformal version of it. And then where was the ultra miniaturized? Just a second. See the all the miniaturized versions is basically like it's a 0.1 lambda only. Okay.
Oh, okay, sir.
You can consider it as a 0.1 lambda. Even in that case, you can see whenever you are making it, you slightly reduce it to 0.09. Okay.
Okay,
So
sir.
somebody was asking me that the previous participants that the shielding effectiveness. See, it is basically transmitted signal by incident signal, right? So if it is the transmittive FSS, that is the concept. Okay. Ultimately, you are playing with the S21 data.
Yes, sir.
Yes.
Next question is that conformal FSS bending is simulated as such in the PPT, sir?
I didn't understand the question. Uh, as
In,
such in the PPT, yes, 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 yes. I have shown you the one part of the structure, right? Where I have shown, yes, here you can see that. Okay, so this is one one. See, conformability. You have to consider one thing. You have to take the arc of it. One unit cell simulations won't help you the conformability. Here, one, okay, good question actually. So one unit cell is this, and array comes on top of it. Are you understanding? You can see that one curve is one unit cell that needs to be simulated. Then you are making an array on top of it. Then it looks like this. Clear? One, to simulate the conformal FSS, you cannot use a single unit cell. There you won't get any conformability. To make the structure conformal, you have to conformal that structure based on the given radius, and then you should start your simulation. Okay, here you can look at the electric and magnetic field things and the wave propagation vector, right? So with that, it is basically like your structure is basically growing on top. That is making an array. Uh, are you understanding whatever I said?
sir. Yes,
Is
sir.
that clear? Yes. Here it is one unit cell means not single unit cell. Conform for two conformal FSS, one unit cell means one ring or one half ring you can consider. Because here it is one half ring, not a circle. You can't see it from here, but you can, if you look at this paper, you'd see that it is basically like uh, one half cycle.
Understood, sir.
Yes.
Sir, I think no more questions are there, so that participant can share that screen and ask the question further.
Yes.
Sir,
Just a second. I stop share my screen?
no, sir, no, sir, wait.
Huh. I think I stopped sharing my screen, right? Is it so?
Yes, okay, sir.
Ah, okay.
Yes, sir. Sir, this is the paper.
Mm.
Hello.
Hello, I can hear you.
Yes, sir. Sir, this is the paper in which the metamaterial absorber for EMI shielding application.
Mm.
Okay. This is the structure of the metamaterial absorber in which the ground plane is present.
Mm.
This one, the ground plane is here.
Uh,
And that's why.
just a second. Somehow your screen is. Okay. Okay.
Yes, sir.
Now I can properly see. Yes.
Yes, sir. There is a ground plane which is present.
Mm.
That's why he is
Mm.
saying S21 will be 0. The
Mm.
transmittivity or S21 will be
That is
0.
true.
Okay.
Correct.
Now this is the complete equation for this shielding effectiveness,
Huh.
where the
Mm.
reflective type of SC and
Mm.
absorption type of SC both are in a summation way. So the
Mm.
final equation is this equation
Mm.
number 5,
Mm.
in which
Mm.
when I am solving this equation, the S11 terms are cancelled out. Only the S12 terms are present here.
Mm. Huh.
Okay, sir.
Okay. So what is the question? Can you please tell
Sir,
me? I can see.
my question is, when this SC is only calculated with the help of this S12 and it is already showing this S21 is 0,
Mm.
that means for the calculation of SC, we have to remove the ground plane.
Oh, I have to see it. I mean, it's difficult to comment directly from the formula. I'm seeing it for the first time. I didn't see this paper before. Okay, so there
Okay, sir.
should be some logic behind it. Okay, so
Yes, sir.
what
That's
is
why.
because you have read this paper, I didn't read this paper, right? So,
Okay, sir.
what is ACR here? Reflective type case. What is R stands for? ACR,
Sir, R is for reflecting,
reflecting. Okay, and A for
A for absorption.
absorption.
Yes, sir.
Okay.
And then the summation of these two will give the total shielding effectiveness.
Mm. Okay.
But my doubt is the transmittive term he is showing S21, okay,
Mm.
which generally we all know. But here
Mm.
the SC term in the SC formula there is S12, not S21.
Mm. Mm.
So how this S12 will come? That is my question, sir. How we will take this S12 if the ground plane is completely filled with complete metallic ground plane?
So in their design, they have that complete metallic ground.
Sir, means whenever he is
Do
trying
they
to say
have
about the
complete metal ground over here?
yes sir, yes sir, complete ground plane is there.
Then H21 will be 0.
Sir,
Then
when
your
S2
H21 would be 0, na?
sir S21 will 0, so then SC is also
Would be
not
the
defined.
only. No, then your AC would be 10 log of 1 by 1 minus S1 square. The first part of the formula.
Okay, this one only.
Huh. If I don't know if this formula is correct, then you should not have the second term. I don't
Yes
know
sir,
that whether.
in many of papers I have
Sorry,
seen this type of equation.
somebody is saying some.
Dr. Komal, Dr. Sarthak
Huh.
here. Actually, let me clarify this question. Whenever we are talking about this absorber or PCR with reflective PCR with complete metallic ground plane, the transmission term will be always 0,
Hmm.
right? And if we convert this equation, because shielding will come either through the reflection part or the absorption. We don't want the transmission. Am I right? Hello?
Yes, you are audible. Yeah,
Yeah,
go ahead. Yeah.
yeah. So if our metallic ground plane is there, so there will be no transmission. And if we convert this log equation into linear, we are left with 10 log 1 upon S12 square for shielding effectiveness, which you have also shown in the slides. That is your transmission upon incident signal, E, ET upon EI. So if there is no transmission, so there will be 100% of shielding effectiveness, in my opinion.
Exactly the same thing I said, right? So, but I don't know what is your question. Sorry, what is your name? Is I can see EICT Academy.
No,
Uh,
my name is Dr. Sarthak Singhal.
Oh, Sharthak. Okay,
Yeah,
okay. Yeah,
yeah,
I told him the same thing actually. So
yeah.
this the first part of the expression, I don't know the validity of these expressions because I have not read this paper. But from my understanding, only the first part of your expressions will be valid. Second part will not be valid if you are treating the surface as an absorber.
But even if we are talking about only first term, then only we are not left with anything. Because if we are making this S12 to be 0, it will be infinite. Second term,
Hmm.
okay. And if we are converting this entire equation, because this is the standard equation taken from multiple papers, it has been
Hmm.
quoted in multiple papers.
Okay.
Okay, so
Okay.
and
The
if we are
same
convert,
expressions, huh?
yeah,
Okay.
same expression.
Mm-hmm.
So if we are talking, because actually this 1 minus S11 square is simply the power uh, absorbed by the surface, as much I
Hmm.
understand. Okay,
Correct.
so
It is basically it is basically the when you are talking about the effectiveness, it is
yes,
basically the 1 by of absorbability, right? That is the effectiveness,
yeah, that should be.
right? So so it's basically the when your effectiveness has to be inversely proportional with the absorbability. Now, when you are making it in a log scale, it is like 10 log of 1 minus of S1 squared.
I think
That's
it
it.
should, no, in
Hmm?
my opinion, it should be equal to that of your absorptivity.
Which one?
The shielding effectiveness could
Hmm.
have only two terms, in my understanding, either through
Hmm.
the reflection part or the absorption,
Right. Right.
right?
Right.
So if there is no, and if we say there is no reflection, then
Hmm.
it is completely getting absorbed if it is providing
Hmm.
the shielding effectiveness. So
Hmm.
it should be totally equal to the absorptivity.
I'm not getting what. So you what are you saying? So your
I am
absorber.
saying, I am saying that if there is no reflection,
Mm-hmm.
right?
Mm.
So if Vikram, kindly scroll the paper little up. where we can see the just like show the equation of absorption and the shielding effectiveness. Equation, yeah. Just below the equation 1, the absorption is given by 1 minus S11 omega square.
Hmm. Hmm.
If the
Hmm.
this S11 is 0,
Hmm.
so the absorption will be 1,
Hmm. Acha, acha, in that sense, correct. Sorry,
right?
right. Your shielding effectiveness has to be identical to the absorbability, right? That is
Absorptivity,
true. Yes, that is true.
right?
In log scale, yes, correct.
Yeah.
True, true.
Now,
Sorry, didn't miss
no,
that
it's okay.
equation number 1. Yes.
Yeah.
Huh,
Mm. Now, Vikram,
okay.
kindly show the shielding effectiveness plot and the absorption plot.
So this is the plot for absorption,
No,
the
Mhm.
red one.
right. Okay.
The 4 peaks will come. And this is the shielding
Shielding
effectiveness
effectiveness.
equation.
Hmm.
So both the things are quite contradictory to each other, as we have seen the papers.
Hmm. Why, by the way, why are you following this kind of paper? I mean, I without reading the paper, I'm saying, but you should see the IEEE published. There are many IEEE transaction
No,
papers on the observer. Huh?
we are seeing the papers in IEEE transactions also, and
Mm-hmm.
even in those also we got similar doubts. We have seen
Mm-hmm.
the same thing in IEEE transactions also.
Okay. Hmm. So, from here, what is the doubt? What is the question? Can you please repeat?
The shielding
So,
effectiveness is completely different from the absorptivity. Even in this case, the transmission will
okay,
be S21 will be in 10 to the power
okay.
minus
So,
65.
in that case, I am requesting to the student. Okay, if you can
Yeah.
share me this paper, let me read it
Okay,
because
sir.
I am seeing this paper for the first time.
Okay, sir. No issue.
So let me go through the paper and then probably I will be able to comment on it
Okay. Sure,
because
sure.
it is not ethically right. I can comment just like that
Yeah,
without
yeah,
reading
sure.
the
No
paper.
issue. No
Okay,
issue.
or
Yeah.
if you can scroll up, if I see the title of the paper, I can also download and see. Can
No,
you
we
please scroll?
will use the paper. No issue. We will share.
Just scroll up. Let me see the title. Double elliptical resonator based quadruple band metamaterial absorber for EMI shielding applications. Okay. I am noting down the paper. I will definitely read it and comment on it. It is
Yeah.
published in which journal?
Alexandria Engineering Journal
Okay.
from the Algeria.
Okay. So I will definitely go through it. Let me first see that paper, what they are
Yeah,
talking
sure.
about. Okay.
Yeah, sure.
Otherwise, it
No,
would be
no, it's okay.
difficult.
It's fine.
Yeah.
Okay.
Yes. So, and your contradictions, you are finding it between the absorbability and shielding effectiveness. That
Yeah,
is the doubt, right?
right.
Good. I'll
Yeah,
give more emphasis while reading on that.
yeah.
Yes.
Thank you. Thank
Yes. So the straightforward way to tell, especially to the students so who ask this question. So see, what is your name? Just so that I can.
Vikram
Ah,
Maurya, sir.
Vikram. Vikram. The point here is that whenever you are making the absorber, okay, it's
Yes, sir.
basically like you always know there is no ground plane to the backside of it, right? I mean, no, not ground plane. No, sorry, there is always a ground plane to the backside of it, right?
Yes, sir.
So to
Yeah.
make the S1 identical to 0. So ultimately, what is the concept that you are dealing with? As I said, it is basically you are making an impedance matching surface,
Yes, sir.
right? So main important point here is the absorbability.
Okay.
Okay, so whether you are getting the 100% absorptions or not, considering the fact of real and imaginary part of mu and epsilon,
Yes, sir.
right? So
Yes, sir.
that those are the important parameters. If you are getting that, then obviously you would be reaching to the maximum absorptions.
Correct.
Now I am as if just from the discussions I had some idea about most likely you are working on the FSS in your PhD or master program, right? What is your
Yes, sir.
PhD are you a PhD student or master student?
Yes, sir. Yes, sir. I am a research scholar in NIT Jaipur, and my
Okay,
topic
okay,
is terahertz FSS
good. So
absorber.
in that case, when you are making an absorber, what we have seen in our lab also, I can suggest, so shielding effectiveness that you are seeing it is one more thing. Other thing is that you please see the temperature distributions also on that FSS surface. Okay, so how will you
Temperature.
see temperature distribution? Because see,
Okay, sir.
FSS is continuously getting the signal, right? I think you will
Yes, sir.
get it in one of our journal papers. Okay, FSS
Yes,
is
sir.
continuously absorbing the electromagnetic wave. Now, how the temperatures, now basically like how it is dissipating the signal. So basically like ohmic heat dissipation, correct?
Okay.
So now
Okay.
you illuminate the surface with the same source, and you can use an IR camera
Okay,
to
sir.
see the temperature distribution. That would give you the actual story about your design.
Okay, sir.
See, the base thing is always, Dr. Sharthak, you can, I think you are the supervisor of the students, right? Who is your supervisor?
Yes, sir.
Huh?
Dr. Sarthak Singh
Okay.
Garg.
So basically, like you can see that profile of the temperature distributions on the absorber. That would give
Okay,
you
sir.
much more clear understanding. Okay.
Yes, sir.
That's all I wanted to say. And you please send me this paper, or I will also download it. I'll go through it, and definitely I will comment on it. Okay.
Yes, sir. Yes, sir. I
That's
will
all I
send
can
you.
say. If this particular paper was read by me, probably I would have tell you, but I didn't see this paper before, because there are many papers on absorber, right? So it's hard to remember which
Yes, sir.
paper talks what. Yeah.
Yes, sir. Understand.
Okay. So that's also any doubts from the discussions. I hope that you might have seen some of the case studies about the FSS from the very basic to some of the advanced. Hope this will
Yes.
be useful for your PhD.
Yes, sir.
So
All the
that,
designs we have learned, sir. Sir,
thank you.
session was
Yes.
very good.
Thank you, sir.
Participants, if
Thank
you
you.
have more queries, you can ask. Sir,
Okay, I can see a question. Suggest a book. One book I can always suggest to the participants to read on FSS is the B.S. Monk book on FSS. Don't start design the FSX without reading that book. Okay,
yes, sir.
MUNK. You will get that book in Google also. I'm just chatting in the chat box. I'm writing it. Okay, so Professor Monk, who has written an excellent book on the FSS, please go through it, at least few chapters, to get some insight about the FSS. I have seen one chat in my chat box. I find, and somebody asked, right, what is the book name? Okay,
Yes, sir.
yeah.
Sir, on behalf of EICT Academy and Department of Electronics and Communication Engineering, MNIT Jaipur, sir, thank you very much, sir, for sparing the time for sharing your research work and technical insights. And sir, it was very much helpful to everyone, sir.
Thank you
Thank you
very
very
much.
much.
That was my intention. Okay, so I wish you all the very best. Okay, keep working and keep working on the FSS to some practical, with respect to some practical applications. Okay,
Yes,
so thank you very much. Thank you all, and thanks for giving me this opportunity. Okay,
thank you, sir.
thank you, Sarthak, Dr. Sarthak. Thank you, Dr. Reena Kumari, and thank you, Swati, for giving
Thank
me
you,
this
sir. Thank
opportunity.
you so much.
Okay, shall I leave the session now?
Yes, sir.
Okay, thank you all.